In the name of Almighty God, I'm Master Sankosha, and today I want to talk about cyclic voltammetry at a macroelectrode in one dimension. Cyclic voltammetry is a common analytical technique for investigating electrochemical systems. In this method, the potential difference between a working electrode and a reference electrode is swept linearly in time from a start potential to a vertex potential and back again. See Figure 10. The resulting current at the working electrode is recorded and is plotted against the applied electrode potential in a voltammogram. You see Figure 10 illustrates potential of the working electrode during one voltammetric cycle. The potential is cycle between the vortex potential 0.4 volt and minus 0.4 volt. The scan rate is 1 millivolt per second. You see that the x-axis is times per second and x-axis is electrical potential based volt. Voltammetry is a valuable technique because information about both the electrochemical reactivity and transport properties of the system can be extracted simultaneously for quantitative interpretation of voltammetry. However, we must use numerical methods to solve the physical equations that describe voltammetry. Then unknown physical quantities in the system can be inferred by fitting to experimental data. This example demonstrates the use of a common approximation in which a large electrode, a macroelectrode, is assumed to have uniform transport behavior across its surface. So only physics occurring normal to the surface need to be considered. By simplifying the model to one dimension and efficient time-dependent analysis is possible. In this model, a parametric sweep is used to compare voltammetry recorded at different voltammetric scan rates. Now I will go through model definition. The model contains a single one-dimension domain of length L, which is the maximum extent of the diffusion layer over the duration of the voltammetric experiment. A conservative setting for L is set to greatly exceed the main diffusion layer thickness. L is equal to 6 squared dt max. Here d is the diffusion coefficient of the reactant and Tmax is the duration of the cyclic voltammograph. The domain equations. We assume the presence of a large quantity of supporting electrolyte. This is inert salt that is added in the electroanalytical experiments to increase the conductivity of the electrolyte without otherwise interfering with the reaction chemistry. Under these conditions, the resistance of the solution is sufficiently low that the electric field is negligible and we can assume phi is equal to zero. The electroanalysis inference implements chemical transport equations for the reactant and product species of the redox couple. Subject to this assumption, the domain equation is a diffusion equation, also known as fixed second law, to describe the chemical transport of the electroactive species A and B, which is a different partial differentiation of CIT is equal to di delta C. Boundary equations. At the bulk boundary x is equal to L, we assume a uniform concentration equal to the bulk concentration for the reactant. The product has zero concentration here as in bulk. At the electrode boundary x is equal to zero, the reactant species A oxidizes, loses one electron to form the product B. By convention, electrochemical reactions are written in the reduction direction. The stoichiometric coefficient is -1 for B, the reactant in the reduction direction, and +1 for R, the product in the reduction direction. This formulation is consistent even in examples such as this model, where at certain applied potential, the reaction proceeds favorably to convert A to B. The number of electrons transferred N equals 1. The current density I location for this reaction is given by the electroanalytical Butler-Volmer equation for an oxidation reaction as follows, in which cos0 is the heterogeneous rate constant of the reaction, alpha c is the cathodic transfer coefficient, and theta is the overpotential at the working electrode. This overpotential is the difference between the applied potential and the equilibrium potential, formal reduction potential of the redox couple of species A and B. According to Faraday's law of electrolysis, the flux of the reactant and product species is proportional to the current density drawn as follows. Here minus n and Nj is the molar flux normal to the electrode surface, and Vi is the stoichiometric coefficient. This is expressed in the electrode surface boundary condition in the electrolysis module. The applied triangular waveform for the cyclic voltammetry study is specified in the electrode surface boundary condition according to two vortices potential, forming a potential window between minus 0.4 volt and positive 0.4 volt either side of the equilibrium reduction potential, and a voltammetric scan rate. U is volt per second, which is the rate at which the applied potential is changed. In the one-dimensional approximation, the total current is related to the current density simply by multiplying by the electrode area up. Cyclic voltammetry study. In the cyclic voltammetry experiments, the potential applied to the working electrode surface is varied linearly as a function of time. A parametric sweep is used to compare the voltammetry recorded at different scan rates. Results and discussion. The shape of the cyclic voltagram figure 11 shows the relation between electrode kinetics and chemical species transport diffusion. And here, figure 11 illustrates cyclic voltammetry recorded at a macroelectrode. You see the x-axis has electric potential based on volt, and y-axis has a total current based on the ampere. Initially, at reducing potential, the oxidation reaction is not driven and negligible current is down, and the potential is ramped conversion toward the reduction potential of the redox couple. The oxidation reaction is accelerated and current increases. Once the oxidation reaction has consumed the reactant at the electrode surface, the current becomes limited by the rate of the transport of A toward the working electrode. Therefore, a peak current is observed and a higher potential, the voltammetric current falls off at a potential independent rate. This region is termed diffusion control or transport control, and sweeping back toward more reducing potentials, the conversion of the product P into the original reactant. It gives a negative cathodic reduction current. Depletion of the reacting species B causes a negative peak current, and conversion thereafter proceeds at a diffusion control rate. The magnitude of the current on the forward peak (IPF) is a common diagnostic variable in voltammetry for fast electrode kinetics, and at a macroelectrode under the one-dimensional approximation, its value is given theoretically by the Randall-Seelig equation. See reference 1 and reference 2 for a detailed discussion and derivation. Here you see IPF is equal to 0.446 NFHC, the square NF divided by RT dV, where I is the electrode area, C is the bulk concentration of the reactant, and D is the diffusion coefficient of the reactant. The square root relationship between peak current and scan rate is characteristic of the macroelectrode cyclic voltammetry under the above conditions. And the references that I used for this literature was written by Compton and Banks, and the name of the article is Understanding Voltammetry, the second edition. And the next reference is Bard and Faulkner. The name of the article is Electrochemical Methods, Fundamental and Applications. Now I'm going to go through model results. If Compton Multiphysics is already open, you can start the model wizard by selecting New from the File menu and click Model Wizard. In the Space Dimension window, click the One Dimension button. In the Select Physics tree, under Electrochemistry, click Electroanalysis. Click Add. This model will solve for the two concentration of a redox cube. Change the default concentration variable names to Ca and Cb in the concentrations table. Click the Study button in the tree Under preset studies for selected physics interfaces, select Cyclic Voltammetry. Click Done when the added study and added physics interface list look as to the right. Global definitions: load the model parameter from a text file. The location of the files used in this exercise may vary based on their installation. For example, if the installation is your hard drive, the file path might be similar to C program files, Console 64, multiphysics applications. Now I want to go to the parameters in the model builder. Under global definition, click parameters 1. Under Linux and Macintosh operating system, the home toolbar refers to the specific set of controls near the top of the desktop. In the setting window for parameters, click the Lab from File button, browse to the application library for the electrochemistry module, then select tutorials and double click the file cyclic voltammetry one dimension parameter text. The figure shows what the parameter list should look like after loading the text file. For any model, you can create your own parameter lists and store these in the text file to reuse them in your models. To create your own text file, click the Save to File button. Now I want to go to the parameters name. The first one is voltammetric scan rate, which is 1 volt per second. The next one is reactant bulk concentration, which is 1 mole per cubic meter. The next one is reactant diffusion coefficient, and the value is 1 e minus 9 square meter per second. The next one is product diffusion coefficient, which is 1 e minus 9 square meter per second. Reaction rate dimensionless is 1 e 10. Electron radius 0.01 meter. Reference exchange current density is 9.6485 E10 ampere base square meter. Double layer capacitance is 0.2 Faraday per square meter. The temperature is 298.15 Kelvin. The start potential is minus 0.4 volt. Switching potential is 0.4 volt. An outer bound on diffusion layer is 2.4 E minus 4 meter. Initial product concentration electrode is 1.7322 E minus 7 mole per cubic meter. And now I want to go through the geometry 1. Build the model geometry as a single interval where the left boundary will later be defined as the electrode surface and the right boundary will be boundary toward the bulk. The interval 1. In the geometry toolbar, click interval in the setting window for the interval type L in the second row in the coordinates meter table. This sets the interval length to L. The value of L is defined in the parameters node. Note that L will vary with the voltammetric scan rate parameter V, which is also defined in the parameters node. This is down to ensure the length of the electronic domain is always greater than diffusion length. In the geometry toolbar, click Build Up. The completed geometry is now built and appears in the graphic window. Now I want to go through the electroanalysis. Start defining the physics by setting the diffusion coefficients for the two species of the redox couple. Electrolyte 1. In the model builder window under component 1, select electroanalysis. Click electrolyte 1. The D in the upper left corner of a node means it is the default node. Locate the diffusion section in the settings window, then selecting the DCA and DCB text fields, type DO and DB respectively. Concentration 1. Set the concentration at the right boundary to bulk concentration. In the physics toolbar, click boundaries and choose concentration. Select boundary 2 only. In the concentration section of the concentration setting window, select the species or as species CB checkbox. In the C row, C all text fields type C bulk. Electrode surface 1. Set up the electrode surface and cyclic voltammetry settings on the left boundary. In the physics toolbar, click boundaries and then click the electrode surface. Select boundary 1 only. In the electrode phase potential condition section of the electrode surface setting window, choose cyclic voltammetry from the leads in the linear sweep rate type V, the voltage will be cycled between the vortex potentials. When the start potential is not specified, the sweep will start at vertex potential to enter the following. E vertex 1 in the vertex potential 1 text field, E vertex 2 in the vertex potential 2 text field, electrode reaction 1. Specify the electrode reaction as a Butler-Wolmers reaction, which is concentration dependent as defined by the stoichiometric coefficients in the reaction. In the model below window, expand the electrode surface 1 node and click electrode reaction 1. In the settings window for electrode reaction 1, locate the stoichiometric coefficient section. In the VC and VCB text field type 1 and -1 respectively, locate the electrokinetic section and type in I0 reference in the I0 reference C field. Double layer capacitance. In the model with the window, right-click electrode surface 1 and choose the boundary condition double layer capacitance. Select the double layer capacitance node and type CDL in the CDL text field. Now I want to go through initial values 1. Continue with specifying the initial concentration values. This will set the concentration values when the simulation starts at t is equal to 0. In the model builder window on the component 1, select electroanalysis and then click initial value. In the settings window for initial values, locate the initial value section in the CR text field type CBulk and minus CB0 multiplied by 1 minus x divided by a in the CB text field type CB0 multiplied by 1 minus x divided by n. The node sequence in the model window under the electroanalysis interface should match this figure. Now I want to go through the global definition. Default model input. Set up the temperature value used in the entire model in the model builder window under global definition. Click, click default model. In the settings window, locate the browse model input section. In the 3D select general and then select temperature. Find the expression for remaining selection subsection in the temperature text field type T. Now I want to go to a mesh 1. The default mesh settings can be used in this model and therefore no change needs to be made here. The next one is studying the problem is now ready for solving. Use a parametric sweep to solve the problem for various sweep rates. Now I want to go to the parametric sweep. In the study toolbar, click parametric sweep. Under study settings, the parametric sweep setting window, click plus, add bottom under the table. In the parameter name column, select V as a voltammetric scanner from the list that appears. In the parameter value column, enter 10 to the power of range, which is initiation number is -3 and the interval number is 1 and until the zen volt per second. In the study toolbar, click compute and I want to go through the results. A number of plots are created by default. The first default plot group shows voltammerograms that are automatically created together with the cyclic voltammetry feature in the electrode surface node. Now I want to go through the cyclic voltammograms. On the cyclic voltammogram toolbar, click plot to see the simulated voltammograms in the graphic window. In the legends box covers the graph, go to the settings window for one-dimensional plot group denoted the cyclic photogram and click to expand the legend section. Switch, for instance, to upper left in the position list. Doing so and clicking plot will reproduce figure 11. I thank you so much for watching my tutorial video until the end. And also, you can download the proper and appropriate capsule simulation file from github.com/masterscript, which is related to this literature. And today is the 4th day of April 2026, and time is